Alright, welcome back from break. Let's dive into rotting oranges. I also updated my slides for that indentation that I missed prior. Alright, so rotting oranges. In this problem you're given a grid. Basically it's an array of arrays sized n by n, meaning that the amount of rows you have isn't necessarily the amount of columns that you have. 0 means that you have an empty cell, 1 means that you have a fresh orange, and 2 means that you have a rotting orange. What's the significance of this? Every single minute, the rotting orange basically will make a fresh orange rotten. And by adjacent fresh orange, we mean that it's four-directionally adjacent, meaning only north, south, east, and west, or up, down, left, right. You cannot go diagonal. So this question asks us to return the minimum number of minutes that must elapse until no cell has a fresh orange. If this is impossible, return -1. First of all, when can this be impossible? Well, this happens, let's say, if the fresh oranges aren't connected to a rotten orange. This can also happen if there are no rotten oranges at all, right? If you don't start off with any rotten oranges, then your oranges stay fresh forever. Yeah, that's this example here. No fresh oranges at minute 0, the answer is just 0. Oh wait, no, yeah, this is different. This is when there are no fresh oranges whatsoever to even make rotten, and there's no, and there's only one rotten orange, right? This is a grid where, whoops, trying to get my pen working. This is a grid where the first cell, it's only one row. The first cell has nothing, and this one has a rotten orange. So you're already done at that point. So make sure to take care of edge cases like that. Like you might have like a fresh orange right here, but then you might have a rotten orange right here, right? And in this case, you should return -1. Because this fresh orange is basically always going to stay fresh, right? So we care about concepts like connectivity. Well, I feel like this is actually not my handwriting, so I wonder if something is like really up with my machine. It's like it's sampling points,
Way
but it
down
can't
sampled.
Yeah, not fast enough. Oh well, onwards. It's been working okay so far. Oh wow, yeah. So in this problem, I wrote a fair amount of code, so I'm probably not going to try and reproduce it live. But I am going to talk about it. Oh, actually, yeah, no, you should take a minute and think about it. So take a minute and think about how you would approach this problem, and if you just want to talk it through, that's fine too. But I'm going to set the timer for a minute, but just chime in, and people who are watching the recording can just pause.
Okay, so the first thing that I had to kind of like explain to myself, and maybe it's painfully obvious, is how does a grid correspond to a graph in the first place? And this four-directionally adjacent condition, that defines adjacency in a graph. So, it's like I just drew a picture here like this, and maybe it's painfully obvious, but each cell in the grid should correspond to a node in the graph, I think, and a node in the graph is adjacent to another node if the two corresponding cells share a side. So you can just rearrange it into like a grid. And I drew one for a grid of nodes with edges, and I drew that for the first example. That's kind of hard to see, huh?
Yeah, no, I see it. No, that's good. That's
Okay.
also how I think about this problem too. When you're dealing with a grid, um, I actually don't make an explicit graph data structure. What I use is the grid itself, and I use the compute and I compute where to go next instead of having an explicit edge. So when you deal with this type of problem, there's no explicit edges, and that's okay. Um, I'll show you a bit in the code. Hopefully, this isn't too much of a spoiler. But what I tend to do is when I go up, down, left, right, I create a list that looks like this. And this just represents the change in row and the change in column. I name those drdc, like in calculus, or I guess not in calculus, it's just the delta. And I just compute the next row and the next column. And what I do is I check whether we are still within the grid. And if we are not in the grid, we can't process it. That node's not valid. So this is how I generally deal with grids and navigate through them. I don't have explicit edges. I just do a check like this in order to check that I'm within bounds. This might be like a bit hard to look at when you look at it at first, but like after reading like a bunch of other people's LeetCode solutions and writing, something that looks like this a bunch of times, this will just become pretty natural for you over time, just to see this as like, oh, okay, they're just trying to traverse to an adjacent cell. So that's what that looks like. But yeah.
Right. And yeah, that makes sense. My point was not I wasn't thinking to construct the graph explicitly, but I guess just to try and be explicit about the connection between
Yeah,
how
no,
you
that's
can
good.
think of a grid with breadth first search, right? So
Yeah.
then it so looking at like the first example, right, we see that, well, not sure what you would necessarily want to be your starting node or cell. But I mean, 0, 0 seems the most natural to start with. You might want to revise that, but then you can look at its neighbors or its children, right? And because it's a 2, you know that any of the ones adjacent to it can be set to 2, according to the rotten orange turns its 2 adjacent cells rotten, and then you would have those. So just do a breadth first search. You would enqueue those 2 child nodes, whatever's, and then we continue the iteration. Check whatever's adjacent to either of them. In this case, we would want to. This is going to be cyclic, right? This is not a tree, so we are going to keep track of which nodes we visited already, so we don't double up the work.
Mm-hmm.
And yeah, I think that winds up being a pretty direct translation of the pattern you were showing, unless I'm missing something. And then so the question then is just, or the result is counting the number of levels you've traversed, I think.
Yeah, that's
Will
the heart of the
correspond
problem.
to the sort of the progression of minute to minute.
Yeah, I agree. It has a uniform cost to traverse to go through each quote unquote edge. I'm going to bring up this example and just draw it out for you. So this is a rotten orange, right? The execution will stop at 1, 2, 3, 4 steps, right? So these will all be transformed, right? What should we return here, though?
-1.
-1, right?
Yeah.
Because this fresh orange never changes. So there's a detail that we'll have to keep track of just how many fresh oranges are remaining, right? Because it's possible to exit the BFS, right? But that doesn't mean that we got everything in that time. There still might actually be fresh oranges out there. All right. How are we doing on time? I remember I planned out some small group work. Oops. Cousins of binary tree, number of enclaves. I think those are fairly straightforward. Anyway, all right. So, good. That's really good. There is one detail to additionally hammer out. And I'm going to give you this example right here. And let's say we have 2. And all right, let's say we have an example like this. Make this a little bit more interesting. Where should we start our BFS?
So if we start at the top left corner, like I was saying before, we're gonna have to check whether it should turn to 2 because it's adjacent to a 2. But if my first guess would be to look for a 2. But I'm not sure.
Okay. Let's say we look for a 2. And let's say I find this one. Is this where we start for our BFS?
I'm just trying to think if it would work. I think it would work if you started there, but I don't know if you have to.
So I'm gonna say something that a little bit alludes to what I've mentioned prior. BFS is kind of like a parallel search. And in fact, if you want to know the time when like maybe it takes for this orange, because this is going to take 3 distance from this 2, but for this 2 it only takes 1 distance, right? And for this particular one, right, at time 2, this is rotten. But if you started from this 2, it would take 1, 2, 3, 4, right? It would take the 4th time, t equals 4, in order to rot. But really, I believe the answer for here is 3 by inspection, because everything is 3 away from at least one of the 2s. So actually, you're really onto something. You want to start at the 2, but not just the first 2 you find. You want to start at all the 2s that you find, because in parallel, all of them can branch out, right? And see if they can enqueue something that's, that's not adjacent. Find if they can enqueue something adjacent, right? And then basically they spread, right? All in parallel. So this is a problem that I've honestly had in some variation from another company asking me about this. And this is a really good problem to practice breadth first search. I think it's actually one of the best on LeetCode, because it really forces you to understand a lot of different things about the breadth first search. So first of all, noting on things that, whoops, browser is slow. It wasn't slow last time. That's too bad. Yeah, the 4 things to get right is you want to know what each node is in the BFS. Here it's simple. We're still keeping it simple right now. And you want to care about what the starting elements for the queue. In rotting oranges, it's wherever you have the 2. And we'll look at conditions for pruning a child, which we'll also practice here, and how to keep track of which ones are visited. All right. This is actually a fairly large amount of code to write, so I didn't want to just take up time and do that. So here's what happens. I want to keep track of the amount of oranges that are fresh, so I have a variable for that. I initialize my variables, I create my queue. I basically enumerate over the grids, rows, and columns, and if I find a rotting orange, I'm going to enqueue that. That's line 10. But if I found a fresh orange, I'm actually just going to say, hey, this fresh count, I'm going to increase it by 1. That way, when the BFS finishes, I'll know whether, if there's any fresh remaining, then I can return the amount of minutes the BFS took. Otherwise, the value is just going to be -1, right? So that takes care of that edge case that we talked about in the beginning. I tend to also print the queue as well, just to make sure that I set things up correctly. I almost always do this when I do a problem. It's like, okay, cool, I started 0, 0. And that's because for these problems, and LeetCode is actually generally tricky with its edge cases, it's not going to show you the edge cases that you should come up with yourself. But for here, we actually always start at 0, 0, unless it's the last one where there are no fresh oranges. This is a pretty cool edge case for them to give you. All right, so I have a visited set, but it is also possible, and you'll see this happen in a lot of submissions and other prompts. A lot of people will actually mutate the grid itself. They'll actually mark it as something that you cannot enqueue. For example, they might actually update the grid. They might actually set the grid value that they've just seen into a rotten orange, because you're only going to enqueue fresh oranges when you loop through the grid. So this looks a lot like the format that we saw before. I'm not entirely sure. Oh yeah, because we care about level, right? So I iterate through it as if we're going through a level. That is why I have a nested structure in here. If you did not care about the level, or if you wanted to carry metadata into your nodes in order to keep track of the level for where that node came from, you don't have to do this inner loop, but I tend to like to do this. It's just something that I got used to, so I'm going to show you that. So one thing to note is, what are my nodes and how do I represent them? My nodes are actually going to be tuples, or tuples, depending how you want to pronounce them. They contain both the row and also the column. It's row first, then column. So in the queue, right, I have these starting nodes. And from these starting nodes, I'm going to look level by level in my expansion. When I pop, Python allows us to do this quick little destructuring I, j to get that row and that value. I know that if this is a fresh orange, then I'm going to decrement my fresh count. If my fresh count is at 0, I know that there's nothing for me to look at anymore, even if the queue still contains elements, right? I don't need to search any further. If you wanted to, you don't have to do this. You could just allow the algorithm to exhaust if you wanted to. So I don't think this is strictly necessary for you to do. This is just enqueuing children from the 4 directions. I do it like this. So once I have this delta for the rows and columns, I just will basically, for each of these possibilities, I put them in a for loop. This is why it looks so nested. And the next row is going to be, well, the current row plus the change in the row. And the next column is going to be the current column plus the change in the column. And if that's less than 0, if the next row or next column is less than 0, then I know I have to not consider this. If the next row or next column goes out of bounds for the max row and max column respectively, I also can't consider this as a valid node. If the next grid or next column, however, contains something that's not a fresh orange, I also cannot enqueue it, right? There's going to be empty cells. It doesn't make sense for us to go to those empty cells because we cannot travel along those empty cells. So that's why this guard is there. I now check if I've previously enqueued this next row or next column. And if I have, I'm also not going to care about it, right? So I put all my conditions for when to exclude first, and only then at the parent node do I decide that, hey, I'm going to say I visited this. And here, visited is also synonymous with like seen or processed in a way. This isn't always true in other types of search algorithms like Dijkstra, which we're going to talk about in person next week. So now that I know it's valid, I'm both going to say, hey, this visited node should be enqueued. And I'm also going to mark that in the visited. The reason why that's important is, let's say you're at a node like right here. These are your parent nodes right now. If you want to enqueue this child, and if you don't do the check for visited here, it is possible to include this child twice, right? You could potentially 2 times that, where you don't need to look at it. So you want to do this check in addition. Like, it also helps you with not accidentally backtrack to a previous node. Once you're at this node, you don't want to go up to here or go up to there, right? This visited set helps us with that. Alternatively, of course, you could actually just straight up modify the grid so that there's no way to enqueue it. Maybe you just start marking them as empty cells, for example. So that's another possibility, but in the general case, I'm just going to use a visited set. So these are all the neighbors, they're enqueued, and I'm not sure. Oh yeah, I decrement the number of nodes that I've seen now for the current generation. When the number of nodes that I've seen in the current generation is 0, I know that I've exhausted the current level, right? That's why this nodes minus equals 1 is here. And then once I've seen all nodes in the level, I know it's time to increment the number of minutes because we just took 1 time for that level. And that's basically it. That's the problem. There's a lot of other problems where you'll BFS over grids. I believe we'll practice that a little bit in the small group work. As usual, I kind of realized I would probably run low on time. I'm going to show you cheapest flights within case stops. I feel like Firefox is frozen. Well, there we go. We're back. But any questions on this one? All right. I would still recommend.
I see the idea. It's the details.
Yeah, the details are what you want to practice for sure.
Okay.
Once you get practice writing BFS, like maybe 10 times, it's gonna start feeling boring, which is good. You wanted to get until where BFS is like you can just implement it, right? If you needed to, because you're gonna see BFS as parts of harder problems. You might run a BFS first in order to actually pre-process something so that you can run another graph algorithm on it. But I believe, yeah, rotting oranges is one of the best problems to practice with. So anyway, next up is cheapest flights within K-stops. I'm skipping one of the problems because I don't feel like we have enough time. Here I'm going to show you SPFA. It is a variation of Bellman-Ford. So this problem, I'm going to say when I first did it, I've submitted quite a few ones to this, and solutions that I've had working in the past no longer work. I've actually resubmitted the same solution and find out that there's updated test cases where my previous solution just would not work, right? This memory limit exceeded surprised me, but I'll go over why this happened. Yeah, but I'm gonna give you a chance to first look at the problem, and I guess if you're live with me, you can talk with me through it. But if you're watching a recording, just feel free to pause. This is 787, cheapest flights within K-stops. It's not an easy problem. There are n cities connected by some number of flights, and just from the diagram, you can see that this is a directed graph. Okay, it's not bidirectional. You can't take an edge both sides. The edge only goes one way. On top of that, these edges have weights, and you're given an array of flights. Basically, these are the edges of this graph, from and to, and there's an associated cost price here. And it indicates that there's a flight from sub I to sub I with cost price sub I. In addition to these edges on this weighted graph, you're going to give a starting position, an ending position, and you're also going to be given K. And K is the maximum number of stops you are allowed to take. Okay, and you want to return the cheapest price to source to destination within K-stops. There might not be such a route. In such a case, you return -1. This is a tricky problem, I'll say, especially if you're new to algorithms, especially if this is like your introduction to breadth first search. This is non-trivial to come up with. For this problem, you might realize that when you traverse a graph, the cheapest way might actually cost more stops, right? But the pricier one is the one you'll return, right? If this is source and this is destination, and let's say this is 100, 100, 100, and this is 300, 100, if your K is equal to, let's say, oh, and this is something you have to know about this problem that might take you a little bit to figure out. Starting at source does not count as a stop. Going to destination does not count as a stop. Okay? So K is really the number of intermediate nodes you're allowed to go to. So in this case, you return for this problem 400, even though 300 would be a cheaper way to get to the destination. If you're only allowed one stop, then 400 is what you would return for this mock problem here. So also note that source never equals destination. This might be helpful for you if you care about not having to do that check during initialization of the problem. You are also going to have 100 possible nodes, and the edges that you might have might be as big as roughly 100 squared-ish. Cut by half. So that's the problem size you're dealing with. So yeah, any ideas?
Sorry, it's
Cool.
just me and I have to
No
think
worries, no
about it.
worries. Yeah, just keep thinking.
Um, I mean, you know your starting node. You're clearly going to have to um, look at all the outgoing edges from
Mhm.
that node. My first guess would be to try and do it greedy, but it's hard to guarantee that that would work. So, like, I mean, the reason to, the idea behind wanting to go greedy with it would be to avoid having to check every single possible path from source to destination. I'm not sure if that would quickly become intractable or not. I guess that would depend on the number of edges. Um, and, or not intractable, but impractical, I mean.
Right,
And,
right.
uh, I don't know, one first thought was like if you get to, this isn't very systematic, but just kind of spitballing, like if you are comparing between the costs of a certain number of paths, if you find that one of those paths is the length of that path is greater than or equal to the number of stops you're allowed to take, or, well, the number of stops so long it is greater than, then just set it to then calculate any outgoing edge from that path, just set the cost of that to like infinity, would be one thought. Is that clear? That might have been hard to parse.
I think I caught the gist of it. When you say you want to prune, I mean, when you say you want to set that the cost of that path to maybe infinity, I kind of think of that as like maybe pruning a path if the number of stops is greater than the number that you're allowed.
Right, just stop comparing with
Yeah.
that. Right,
So
okay.
we're going to see a variation of a way to do this with breadth first search, basically. As alluded to before, this is called SPFA. It's called shortest path fastest algorithm. You also mentioned an interesting idea about greedily trying to take maybe lower costed edges at each vertex. Um, I didn't maybe quite listen in on like maybe the full idea of that, but there is a way to actually use a greedy algorithm over this graph. We're going to see that next week. It's called Dijkstra's algorithm. And Dijkstra's algorithm is both greedy algorithm and it's also a dynamic programming algorithm. It can be formulated in both those ways. We're actually going to focus on BFS and we'll have a chance to look at this problem again using Dijkstra's next week. So this is actually quite long to code, so I have some pre-baked stuff here. Okay, I actually wrote out Dijkstra's in this case. So I'm going to bring out the non-Dijkstra version. Non-Dijkstra version, where are you? you can see that I got it wrong recently, even though I've done this problem quite a bit. All right, so go to editor. All right. So I'm gonna claim that this is basically doable using the breadth first search we already know, but with a few other interesting ideas. Okay. So you'll see this construction again. Hopefully this looks familiar. I care about not only the queue, but I also exit after a certain amount of levels. It's also, I'll go over this probably more next week, but it's also possible to keep the number of steps into the metadata, quote unquote, of the node that we're at. But fundamentally, let me give you a brief overview of the idea here. I built the graph from the edges, and I know that I start from the source node. I'm also probably not showing you like maybe the cleanest code, but the way we screen out neighbors is very interesting. I'm not actually going to use a set here. I'm actually going to use a cost table. So this cost table, which is named the destination of min costs, actually holds what is the min cost seen so far to arrive at the node. So the costs for maybe 3, it might change over time as I update this table. How does that change? Well, I might find a path from 0 to 1, right? And this is the lowest cost path to 1 now, right? So I save that. I'll save that in my table right here. And then from this node, right, it has an outgoing edge, right? This 2 right here. And this one's the lowest cost that to get to this 2 is actually 200, right? I'm accumulating all the cost weights to get to this 2. So you'll see this as for the current node, what I bake into these, I call it a destination node. Everything it has its like original node value, like 0, but I also bake in like the price. And that's the price that's accumulated along the path to get to it. So this is what I mean by like holding on quote unquote metadata and actually being very clear about what your nodes actually represent. Oftentimes when you do algorithms like this, your nodes will carry some sort of quote unquote metadata. So this 1 right here, when I pop it, it's like these values right here, they're from the class destination. If you wanted to use a tuple, you could do that too. I maybe would have used a tuple if I wasn't translating this code from Java that I wrote originally. But yeah, these could be tuples of just the actual destination and the price that it took to get to that current true node, right? These destination nodes, they're like kind of wrappers around what the true node actually is. The true node is actually just an integer, right? And the heart of the problem is really when I pop these things, I can look at, and I look for the neighbors now. If the current price plus the price of the neighbor that I know of in the graph is going to exceed what I have seen before for visiting the neighbor prior, I can prune the child. So you can prune in the parent node, not from a visited set, but you can prune via just the minimum cost that you've taken to see in there. When I create this minimum cost table, I set everything to infinity, right? This table, I used a dictionary, but you could also use like a list if you wanted to. But yeah, I set everything to infinity. So if we first visit the node, then this will be the lowest price that it took to get to that particular node. For 2, the price was infinity when I did the lookup. But now I can update the price, right? I update the table to 2. So this cost table is basically what we saw in the same structure for BFS. This is basically our visited set. But instead of like only strictly allowing us to visit like that node one time, we allow ourselves to visit it maybe multiple times, possibly, if there is another route to that node. You'll see this happen when we visit 3, right? Or maybe not, because k equals 1, right? You're only allowed 1 stop to get to this node.
Can you say that part again? The cost table is substituting in for the visited set, or it's performing a similar function for us. But you can wind up visiting more than one time, you said.
Yep. Let's say, for example, this... Yep,
Uh-huh.
Keep going.
No, that was as far as I understood.
All right, so let's say in this example right here, instead of k equals 1, I'm going to change it to k equals 2 for this particular problem. What happens now is, so this 2 gets visited, right? And so basically when k equals 1, we visit this 1, right? In the first generation, we only had this in our queue. We had this 0 node, right? Then we visit all its neighbors, right? It only happens to have 1 neighbor. So we have this 1 right here, right? We now visit all the other neighbors, and now we have 2, that node, and we also have 3, right? When we process this generation with k equals 1, we basically will exit the loop, right? And because 2 isn't 3, we've never updated getting to 3 from 2, okay? But when k equals 2, we're allowed 1 more generation, right? So this 3 actually has no outgoing edges, so it is actually not... okay, sorry, let me back up a bit. So the queue looks like this now after we visited 1, okay? Now what happens next is 2, right, will enqueue so 2 gets popped off, right? Now the queue looks like this. It only has a 3 inside. It will enqueue 2 things. It is actually going to enqueue the 0, right, because it has a neighbor. And it also will enqueue 3, right, but at a different cost. And associated with each of these nodes, right, this 2 is really a 2, 200, right? This 3 is really a 3, 700. Right? Because we're associating costs along each of them. Because when we pop off the element, we care about like the current price, right? We have this in a data structure. It's just a node with a price and a destination property. We care about the price it costed to get to that node, right? It's almost like you're dealing with, not to get too far into the weeds, but like it's almost as if you've basically transformed this graph into a different graph with different nodes. But essentially, because you carry around that node with how costly you got there, you're able to actually see that, hey, this 300 that gets enqueued gets a cost of 100, 100, and 200. So this isn't just a plain 3. This is actually a 3, 400, right? Which is less than this 3.
Keep
Going.
I'll make sure I'm understanding that when we get to this, I think it's the 3rd generation, the state of the queue at the bottom, that first 3 is associated with 700, that 0 is associated with 300, because it's the cost of going through from 0, 1, 2 back to 0.
Yep. all the
Okay.
cost gets
And
accumulated. Yep. When we enqueue
right.
the node.
And the second instance of 3 corresponds to the path from 0 through 1, 2 to 3.
Yep. This is
Right.
that.
Okay.
This is this 3.
Okay.
And so what happens in shortest path faster algorithm is that we do this pruning right here, right, while we're at the parent node. We see that at the parent node, there's no reason to keep going down a path if we've visited this node at a cheaper cost, right? That's not
Right.
this example. I could have probably, or pre-baked an example that I would have drawn, but I didn't do that. But hopefully you can see that, like, if you end up finding that exact neighbor, but you've gone to that neighbor at like, but if the current way you get there is actually greater than the minimum you've ever seen, there's no reason to keep going, right, through that neighbor. You can just not look at that at all. So
Right.
this basically takes the form of a visited set, and you'll see this happen also in Dijkstra implementations as well. This is an even more general way to screen things out, is by weight. But for simplicity, I put in the pattern just to use a set because this is basically kind of what it accomplishes. All right, there's one edge case here. If you're in Python and if you did not use a default dict for the graph, it's actually possible that like some nodes, like 3, have no neighbors, and you'll run into a null pointer exception when you try to loop through the neighbors in the graph, because the graph was never built with any outgoing edges from the 3. So that's one detail that you got to take care of. And that's basically SPFA. You might see the node multiple times, but each time you see it, it will have happened from a different cost. And that allows you to limit basically the amount of search space that you need to do for this.
Could
I
you
have...
maybe...
Go ahead.
I was wondering, you said it might be too into the weeds, but it might help me to understand, to talk about how you're transforming it into a different graph.
Sure. If you look at these nodes right here, we're actually doing an exploration over a different kind of graph at the same time. Because if you enqueue, let's say 0, then its cost is 0 because you start off, right? When you explore this graph, right, let's see, does this graph have like multiple edges? Are there duplicate edges? There will not be any multiple flights between 2 cities. Okay, so there's not multiple edges for this problem. So this is a node 0, 0, right? These are technically the nodes that we operate with, right? The metadata is now part of the node. For this 3 that we saw, right, it's possible to actually arrive at 3, 400. It's also possible to arrive at 3, 700. You can actually view these as different nodes along different paths, right? This itself is a node in a different graph, right? And you're actually traversing through this graph of tuples, right? It's just that these nodes were not given to you explicitly in the terms of edges, like in the diagram that you see. But because you've tacked on this extra, basically variable cost, you're actually going to be walking through a different graph. Right, from 2, 200, you can get to 3, 700, and this graph looks like actually this now. And from 2, 200, you're allowed to get to 0 from with a cost of 300, right? Which is a separate node entirely.
Mm-hmm.
So you can kind of visualize this as like once you do this, you're actually traversing through a different type of graph.
Would it be fair to characterize that as like the search tree that corresponds to the graph?
Yes, every BFS actually creates a search tree.
Right. Okay. I actually find that really helpful to see it transformed into something else. Great, thank you.
Yeah, absolutely. This would be your start node, and this would be your tree, right? It would be an n-ary tree, right? And you'd be looking at things at a certain depth, right? When the depth that you're allowed is k, well, technically, I guess, like, you get to look at, like, if there's only one intermediate level, right? Whoops. I actually switched these numbers around. Yeah, this is what it should look like. When the depth that you're allowed to is only like one intermediate node, you're allowed to get to this 3700. But if you're allowed just one more hop, you're allowed to get to this 3400. And what you really care about is getting to this destination node with the minimum cost that it took. So in this search tree, if you were doing something like this, this is what this BFS would end up looking like. Yep. I'll show you actually how to mess up writing SPFA for this. I believe I have examples in my submissions. Oh yeah, memory limit exceeded. Okay, this is good. This was before I used a cost table. I pruned it using this way, and this same exact solution worked in February of this same year, but they updated it with test cases such that it wouldn't work anymore. Yeah, this is just translated from JavaScript. But yeah, I've actually done this problem and submitted the same solution multiple times in the past, and they just keep updating with test cases. And I think I finally got like the right execution where I don't think additional test cases are gonna give me memory limit exceeded or give me time limit exceeded. It's actually very easy to mess that up in this problem. So how do you mess up in this problem? Here's one way to do it. You don't prune while you're at the parent node. If you write code like this, you can have memory limit exceeded because you add way too many nodes into your graph. Like in the base graph that you see right here, it's possible to like go to a node multiple times, right? And once you have multiple nodes that can go to that same city, this can get really explosive really quickly. So if you write code like this, right, you just create the next graph node without screening them out by cost, even though logically you'll have things correct, you will have a timeout error or a memory limit error. I also actually did prune at the parent if the current node's price is greater than the cheapest price that I've seen, and the cheapest price I only record when it's at the destination node. That's still not good enough. Like, it used to be good enough, but now it isn't, right? I pruned by using this rule. If I have found the destination, there's no reason for me to keep going, right? Logically, if you've arrived at a destination, you're only going to accrue more costs by taking more flights. So that is a pruning decision that is possible. Also, if you've recorded the cheapest price prior, and if you know that the current path that you're taking, even if you haven't seen the destination, is greater than that, then you can just ignore the current node. Both these ways of pruning are not good enough. They're not good enough because you've enqueued way too many children. And the key optimization is that in this type of pruning, you've only pruned where you know the cost of the destination, whereas the pruning that we do like in the code right now is you get to prune at every single node that you've seen before, right? So that's a lot stronger way of pruning. So I don't recommend you write code like this. This is very common that I've seen in a lot of solutions in the past. If you want to write a really proper SPFA, I recommend you do something like this. Is you prune at the parent node. Yeah, so that's basically it. That's the problem. there's one final thing I wanted to note. In this problem, you should do it even though you've seen the solution now. You should work on building a graph if you've never done DFS over a set of edges before. It's just good practice. You don't have to be like me and create like a new class. In fact, if I were not translating code, I would have probably just used a tuple. But basically, how do you build the graph? I use an adjacency list. I use default dict, and for everything that's not found, it's just going to call a list. This is how that even though that getting, let's say, this graph might be empty when I do the lookup for the source because source has not been added before, the graph will actually add a default list, right? If it hasn't been seen before. So let's say the source is 0, right? It'll actually just initialize that empty list for me. That's why you use a default dict with list as your function. And then you can just straight append the outgoing edges, right? When you append the outgoing edge, this can be node 1 and with a cost of 100, right? So that's basically what the graph is going to look like, is basically this structure right here. So practice doing that. You'll have plenty of opportunity also in the future, because there's a lot of problems where you're going to have to actually build the graph yourself. And this is just one very quick implementation of doing that. All right. Let me just walk through my slides a little bit. There is this problem. I encourage you, we're not going to go through this problem, but to try this out yourself and use just a BFS and yeah, see if you can accomplish that. But otherwise, I have some small group work for us to go through right now. The first one is an easy one. It's cousins in a binary tree. And yeah, I guess we can work through this together in the Google Doc if people have time.
Let me just try and pull that up.
Yeah, let me just pull that up to Drive. Yeah, let me try and get to the link. All right, I'll start just talking through the problem while people get that up. All right, problem 993, cousins in a binary tree. Given the root of a binary tree with unique values and the values of two nodes of a tree, x and y, return true if the nodes corresponding to the values x and y in the tree are cousins, false otherwise. So what does being a cousin mean? It means that they're at the same depth but with different parents. Right? And at the binary tree, they're saying that the root is at depth 0, and the children at each, and the children of each depth k node are. Wait. Oh yeah, the children of depth k are at depth k plus 1. Yeah, just feel free to talk through it with me.
It definitely seems similar to the first one with the sums at levels, where we need to know what level we're at, and we also need to know in this case for any pair that has matching values that they do not share a parent. Um, so first things first, we'll need a queue, I presume. Won't let me
Dang,
write all over the place.
I thought I turned off like automatically uppercasing it.
That might be on my view that it's doing that. Is that in tools? Let's see.
I turned
There you
off
go.
automatically
Turned it off.
capitalizing words. Yeah. Oh, I guess. Oh, I thought it would happen for the entire doc. I guess it's per user.
I think it's, yeah. Okay, so I mean it's clear that we can use binary search. So using a queue, or sorry, breadth first search.
Yep. BFS. I know what you meant.
Right, and we have a root node, in fact. So do we have to use a list? Is that the right syntax for initializing the
Yep.
queue?
Yep. A deck can take an iterable. Yep.
Okay. Right. And before, what we had, so that's initialized, and so we're gonna need to stop when we can stop. We want to search the whole thing, so we can stop when it's empty. We'll want to return as soon as we find the matching values, but we'll need to have something similar to the way it worked before. So
Just note that in the problem, each node has a unique value, so you don't have to guarantee, so you don't have to do some weird check about that. Just assume all the nodes have different values for the x and y. And x and y aren't guaranteed to exist in the tree.
They are guaranteed, it says.
Yep, it's part of the constraints. So don't worry about like cases where one of them is missing or something. Don't worry about that.
Every value is unique. We know that it's not going to be the node because that can't be right. And it's a binary tree. So right now I'm really just copying the pattern up.
Oh yeah, go ahead. My first thought is like, why did I put this in the BFS set? This feels more natural as a DFS problem to me. Because if you just traverse through the entire tree, you can just record the two depths, where the x happened and where the 3 happened. Oh, but then you'd have to make sure that the parent is different. Yeah, I guess you could also just keep track of that when you do the depth first search as well. Hold on, I'm actually gonna like take a peek at my solution,
okay.
So I can like guide this. Wow, this is really surprising. I solved this as a DFS problem indeed. I did not solve this as a BFS problem.
So in order to do that, did you have to have, you had to store some extra data for each match you found, right? About what level and what its parent is?
Yeah, it looks like I recorded something about the height. Yeah. I would say, I think I assigned this problem as small group work because there's a harder version of this problem that I did.
Mm-hmm.
And this was the easier. And the harder one I definitely saw, I was like, oh, yeah, I definitely use BFS for this. That being said, now that I look at it, I was like, this is still doable in BFS. And actually, I think BFS might actually be more natural. I'm like kind of backtracking on my opinion right now. So I guess this is going to be a new problem for me to do as well. That's wonderful, because then you can see me make mistakes.
So I'm basically just reproducing what I remember from the pattern before for the sums problem, the sum at level problem. And I'm not sure if that's going to work precisely.
Yeah, it's generally a variation on it, but yeah. I think BFS actually makes more sense in this problem, yeah. You care about, what you're doing right here in this template is, you care about iterating through the nodes of the current level. And by definition, the cousins have to be in the same level with different parents, right? So, same level, different parents. And actually, I think this is the correct pattern to use. So you're processing nodes within the same level. And you just have to keep track of whether you've seen X and Y at the same level, but ensure that they have different parents.
Right. So
I'm going to riff just a little bit on what you have. We definitely care about no.val, right? We want to process it somehow. I'm also, hold on, I'm going to tighten up this indentation a little bit.
Oh yeah,
so we definitely care about no.val. And I think for the things we care about, like very naively, like I try not to do super smart things. I just try to do very simple, understandable things as best I can. So I'm going to have a variable called xscene, and I'm also going to have a variable called yscene, and I'm going to initialize them to false. So I think we have to care whether we see the x or the y at the current level. So I'm going to say, if no.val equals x, then xscene equals true. And I think similarly, well, what's happening to my voice? Yscene can be set to true by much of the same logic. All right, and that's when we process the current level, right? So once we've processed the current level, we'll know that whether x or y has been seen before, right? If x seen and y seen, we want to, check if cousins. But there's an alternate thing that happens, like elif x seen or y seen, I think it is actually fine to return false right now. Because this would mean that you saw one of them at the level, but you didn't see the other one at the level, right? This would not be same level cousins, so you can just return false.
And we set it up that they'll only both be true if they're at the same level.
Right. Yep. If you don't see either of them, none of these pass, right? So you can just keep going on in the loop.
Mm-hmm.
So we want to check if they're cousins, which means that we care about, like, so which parent did they come from? And here, I think this is where I use one of those techniques I've been telling you about, is to just like add in metadata. So this is similar to the idea of BFS. It's like, well, you could record maybe what parent it was, right? For the sake of this problem, I'm going to look at the prom constraints a little bit, and I see that the prom constraint actually has the node value between 1 and 100. So for the root value, I'm going to say its parent is maybe 0. But that's really kind of like a nullish kind of value, right? It's not really meant to mean anything. And now, when I enqueue, I'm not only enqueuing the node itself, but I'll just enqueue the node.val, right? Because every node has a unique value. I will be able to know, basically from the value, that it is that unique parent. So it would just be storing an integer in a tuple, in this case. So in this case, once we pop off, it's node comma parent, right? So how do we know whether they are cousins or not? I think we need to do some kind of check with the parent.
Inside this loop?
I actually don't know. I'm still thinking about that. It just feels like we need to keep track of the parent, right? But if we've seen X seen or Y seen, we need to keep track of the parent. I might actually, in addition to this false, just keep track of which parent it was. And I'm just going to use 0 for a dummy value. So I'm going to set X seen to true and then parent. And I think you kind of can see the rest, right? Do you want to do the rest?
Okay. So similar for Y seen.
Yeah, I guess we have to check now that they're no longer just booleans. We have to, yeah, check the
something
tuple
like
values.
that. And like X seen, not her. There might be a cleaner way to unpack these tuples, but that would tell you if they're not parents or don't share a parent. Or true. Otherwise, yeah, so in this case, in that bottom condition, we do have it set up where I might be inclined to just add some condition on the parent, and we're going to need something else. I mean, we're going to need another condition, I think, if they both been seen, but they have then they're unique values. We know they've both been found, but they're not cousins, so we can return from that. And should we say anything more in this disjunction?
This looks logically correct to me.
Okay.
They have to be the same level, which we've guaranteed by how we loop through this particular queue. You could, instead of breaking this out into another case, it is possible for you to just return this expression inside here and not write this expression. Because once you've seen both of them, you can just return whether like their parents are the same. If the parents are the same, then well, actually, I guess you want to return the negation, right? If they're not equal, then you return true. If they are equal, then you return false. So you could do something like that if you wanted to, but what you wrote is logically sound, right? That has the same effect.
Okay. I see that. And then if we don't hit any of those conditions, then we haven't found any matches, or we found, no, yeah, we haven't found any matches, so we return, or sorry, we continue out in the loop. And I guess if we get, I think, then we just need this, basically. We won't have found any matches. And we'll have traversed the whole tree at that point and not returned anything. That show up?
I'm gonna see if this submission works. But I think basically this is. I think because X and Y are always in the tree, you don't necessarily have to worry about the final return false. But of course you want to, put it there. Just so it looks like it returns something. But yes, by the prom, it's always guaranteed that within the while loop, something will be returned.
Python object if you don't have a return in every branch.
Oh yeah, that's probably true. It's probably true. I ran over at least the given example test cases, and they seem to work. It's too bad that you can't translate tabs into spaces that easily in LeetCode. But I'm going to try submitting. And boom, yay, it worked. Good job.
Great. That was very collaborative. Thank you for your help.
No, absolutely. Yeah, it's what I wanted these small sessions to be like. They're just times to practice BFS together. You might not have enough time, but if you do, I'm willing to do a number of enclaves with you. But otherwise, yeah. I don't know if you've noticed, but I try and keep the lecture problems harder than the small group work. Because it's just hard for me to estimate sometimes, for a harder problem, how much more time might it actually take. All right, but anyway, here is number of enclaves. So we have an m by n. Let me copy and paste that into the chat. But I'll read it out loud. So this is number 1020. This is number of enclaves. So you're given an m by n binary matrix grid. What does that mean? A binary matrix grid means that each cell is either a 0 or a 1. There are no other values in that grid. So a move consists of walking from one land cell to another adjacent 4-directional land cell, or walking off the boundary of the grid. Remember that the number of land cells in the grid for which we cannot walk off the boundary of the grid in any number of moves. All right, let me simplify that sentence. Basically, you want to find the number of connected ones that do not have a connection to the boundary.
All right.
So yeah, this is doable. So think about it in your mind. Would you use DFS for this, or would you use BFS? Well, the answer is you could use both, right?
Yeah. I almost looking at example 2. It seems like one where DFS would be most obvious. But I don't know if that like generalizes more to other configurations because there's just like one path there, where I guess you wouldn't know what path to start on, but if you found some one somewhere and, well, it depends on where you start. So, okay, thinking about this, I think both could work. If it's BFS, then the first question is where to start. And you mentioned this sort of like doing it in parallel by finding, because we're really just interested in paths that involve ones, right? So I'm thinking it's like that problem where we need to find and initialize to start with some ones. But if they're part of the same path, we might wind up doing extra work.
So this problem,
Mm-hmm.
I would say it's definitely easier than rotting oranges. You can do this in a variety of different ways. I think that you'll find better ways to do it than probably how I did it. Let's see, how did I do it? Oh, I don't have anything here. But there's a few general, so you could use either BFS or DFS for this. And even when you use DFS, you're going to have different starting points, right? Because there could be more than one enclave, right? It's just that the order in which you process them, might vary. So for DFS, you definitely start here, and you could start at any one of these, but let's just say that you just also start here. These outer edges are kind of interesting, right? That you don't count them. You want to not count them. In this example, the answer is 2, right? Because you see 2 enclaves, right? This group of ones is completely surrounded by zeros. Is another way to think about the problem. You might actually do 2 different types of, passes, right? Or you could do it in one pass. And what do I mean by a pass? Well, you could start off by looking at all the boundary ones and then just traversing them and then flipping them to 0, right? Flipping them to 0 because they should not count towards the enclaves, right? That's one way to start doing this problem, is to maybe pre-process from the edges. That's one way to do it. Another way to do it is, there's various other ways. Another way to do it is, maybe you don't pre-process. And what you do is, in your search, whether it's breadth first search or depth first search, is that once you start looking, if you jump out, you know that this entire island is not an enclave anymore, right? Shouldn't count your answer. So you could do it either way. And if you were able to DFS and like none of them turned up that way, then you know that it's an enclave, right? So there's multiple ways to approach this problem, but anyway, whether you pre-process or you don't, BFS or DFS are viable options. There's really nothing fancy, like there's really, you don't care about shortest path or anything, right? You just care about exploring adjacent things, right? If those are your requirements, you have more options, right? If it was you needed to find, like in rotting oranges, the minimum time until all oranges rotted, BFS is much more ideal for that type of problem in general than a DFS. You have to know very specific things in order to do a DFS for a shortest path problem. Like you have to know quite a bit about that problem constraint in order to try to do that efficiently, at least. So anyway, I feel like we have an understanding of the problem right now. We definitely still need to find our starting points. Do you have an idea of what general type of strategy you want to go with? Or maybe you've come up with one on your own.
For finding a starting point.
Well,
for the whole thing.
For the whole thing, like whether you want to pre-process from the boundaries and then just flips the ones to zeros, or whether you just want to go through a search traversal and see if you can go out of the edge or not.
I think for our purposes, just not pre-process and just do a BFS.
Okay. I'll note that I'm thinking about it in my mind and I'm wondering, the not pre-processed one might be easier to do with a DFS. And that's because like as you expand, let's say these are the nodes that you found from your BFS, right? You expand, but then it's like, let's say you have all these ones in the queue, right? So you have this one in the queue, you have this one in the queue, you have this one in the queue, right? For each one where you expand, let's say you check here and it's off the grid, right? We're going to have to know to specifically mark these other ones. And that might be hard to do, like if you're just using one while loop, right? You'd have to keep track of like, oh, this came from this. And then you'd have to know that this, like when this gets in queued, it needs to know that it shouldn't like do that or whatever.
Right.
There might also be some complications where like, actually we should think about this, like, because like as we loop through and find a one to start with, we probably aren't going to enqueue like all the ones and then do the search algorithm. We probably actually want to do the search algorithm immediately when we find that one, right? Because unlike the rotting oranges problem, we actually only want to start at one at a time. Just imagine, like, how would you know that this one wasn't connected to this other one, right? If you started this one and this one at the same time, or actually that's not as great of an example. If you start this one and this one at the same time, it's going to be hard to separate those two because they come from different starting nodes, but one should be counted and the other one shouldn't. There might be a smart way to like do that, but I'm not sure if it's going to be simple. So I think in this general structure, like when I work through these problems, I write pseudocode first. Search through for the first one, right? And then do you could do something like a BFS on this problem. But man, I just keep looking at this and I'm like, I feel really drawn to using a DFS. I feel like DFS is actually cleaner because for a BFS, you have to, like, let's say this graph is like here, right? And if we did a BFS and we got to this generation, we lost reference to all these other positions, right? So yeah, then you have to like know to mark this as not an enclave. Wait, no, wait, sorry. This is possible. Yeah, I think so. But you'd still have to mark all the nodes to not look through them again. Sorry, this is probably super confusing. I'm planning to basically...
Could we not throw things into a visited set if we found that they were part of a path that leads to the edge?
Yep, you're right, yeah. We should use a visited set.
So
yeah, no, you're right. And we could mark that particular BFS as being successful or not, right? We could mark it true or false. We could use a visited set. So if, you know, grid of, or let's say if row col in visited, then we just continue, right? That allows us to skip through the nodes as we go through this for loop. Otherwise, we can run our BFS starting from that row and that column, right? And based off of the result, we can do enclaves +1 or not. Oh, you're right, yeah.
Will we need in our BFS though to have, oh, the BFS will check the visited set though. That's defined in that outer scope. Yeah, right. Okay.
For this problem, you could also, like, instead of using a set specifically, you could actually just use a 2D array that's the same size and just mark them true or false inside a table like this. But you can also use a visited set. Either way, it works.
And that would be, you would define, sorry, how would you populate that grid?
The grid would be populated by all false at the beginning, meaning that it's not visited, right? So as we look through each one, the BFS will mark it, right? We'll flip it into true, right? And then flips it to true for each node it looks through. Additionally, we only care, right? There's another condition.
Oh, right.
If row, if grid of row column equals 0, then we also continue, right? Because there's no need to, like, for the outer for loop to care about zeros. There's nothing to BFS there. So we can have these two conditions, and the BFS will update the visited set so that the outer nested loops will just ignore what the BFS has seen. And then if the BFS says, like, oh, hey, by the way, none of us went to a boundary, we can increment the number of enclaves outside.
Right. Okay.
This is kind of running late, but I'm willing to help you through it if you want to go for it.
Yeah, I'd like to try and knock this one out if we can.
Sure.
Thanks for sticking around.
Yep.
So,
I think you care about the indices, so I might either use an enumerate in Python or, you know, something else.
Wait, did I see what you're saying? I don't know. I'm not sure I saw what you were saying. Uh,
No, that's basically what I meant. Um, you might also want to enumerate the row as well,
right.
um, because that'll give you the column index.
Right.
I guess I'll name that J since you named that one I. Yep.
Okay. And we had down, I think it might be easier for me to think about the visited set, uh, the visit as a set than as a grid, I mean to say.
Yeah, yeah,
Um,
yeah, absolutely. I might move that up a
so,
little bit,
uh-huh.
just because you don't want to initialize a new visited
Yeah,
set every time.
absolutely. It's gonna need to be outer on top, yeah.
Yep.
It's gonna be like global to everything we're doing. And then, what did we say? We went from, look at grid IJ. We're gonna basically do, we also want this. And I'm gonna do like temporary.
Mm-hmm.
Is that what we wanted? We were saying EFS. Then we're gonna look at a node. I guess we're not gonna do it if it's visited already. Or is this?
I'm trying to bring out my pen drawing without being in
Yeah,
pen
maybe I'm
mode.
not remembering.
No, that's good. That's good syntax.
We're gonna have, I'm not sure exactly what type of, but it's gonna maybe have it return some condition. Yeah, say it returns true if it finds that it's not connected to the outer edge of the grid, and that's
Mm-hmm.
how we add up our enclaves.
Yep.
And I think then it's just fill in BFS.
Yeah, basically.
Yeah.
That
Okay.
BFS is probably going to take in the coordinates itself rather than the value at the
Right.
coordinate. But that, yeah.
So I'll change that just to. So now the question is, how are we going to do that? We're going to have, well, we're going to. Start with that. We're going to use coordinates for our nodes, our node representation.
Mm-hmm.
Oh, and then there was all that arithmetic you had for finding adjacent edges. Um,
Yep. It's good to implement it at least once, though. So.
yeah, okay. All right, now I'm really on the spot. And it's, right, so it's child nodes for IJ. It's going to be, how did you do it? You wrote tuples.
I'll help you out when we get there. But let's fill out the structure first for the BFS.
Okay. But don't I, in order to get the connected nodes, I need to do those calculations about incrementing, decrementing I and j by one
Mm-hmm.
each and checking whether it's outside the boundary,
Mm-hmm.
right? Yeah, so I mean, I would go ahead and just do a bunch of ifs. I vaguely remember you had a cleaner way of doing it. Um, if and if I plus one plus. Those should be the 4 child nodes. Then oh, I see what you're saying now about fleshing out the structure.
Cool. Yep. You got the queue. Yeah, you don't because you don't care about the levels here. You can ignore having like a nested for loop. Yep.
Right. Thank you. If I minus 1 is greater than or equal to 0, then we need
I'm gonna just destructure that as ij, since you reference I and j. I'm guessing you just wanted to pull out the tuple.
Yes. Yes.
So you've written your conditions, right? If I minus 1 is greater or equal to than 0, it has a possibility of being valid, right?
I think this is what I meant to do.
All right, I'll let you write this out, but
Okay.
yeah, we'll talk about it.
That was not going to work.
I mean, you're still in the process of like getting it down, but yeah. But this is good. This is good. It's really important to make mistakes when you first start off writing BFS. So first of all, knowing what your nodes are, right? Your nodes are actually coordinates, not the actual value, right? So this is the cell value, not the actual coordinate for the cell.
Yeah.
It is also possible when you look at these statements. So if I minus 1, right, if this coordinate, like, you go into the grid, sorry, I think my pen's finicky because like my computer's like not happy today. Whoops, did I? Oh, accidentally did that. Sorry, if you could move that cube back to where it was. So let's say you're at this coordinate. Let's see. Let's say you're at I minus 1, like this coordinate, and it's greater or equal to than 0. Let's say it doesn't matter what the value is, right? Let's just say the value itself is 1, but you're at the edge, right? Or actually no, this is more the example I want. Let's say you have an example like this and you're at this final coordinate, right? So I minus 1 is greater than 0. So Q, well, I guess maybe you could do this, huh? Okay, at least one thing that I feel is off is you used less than or equal to then, Because if you're
Mhm.
actually equal to the grid length, you're
Oh.
actually right here, right?
Right.
If
We're off
you're,
the
yeah,
edge.
yeah.
Right. Good. And
That's a very common mistake. Like just figuring out whether you're going to use less than or equal to than or whatever.
I'm gonna chalk that up to having someone watch me do it. Those mistakes become more common when
They do. They
you're
do
being
so very
watched.
much. Yeah. But these are really
So
good mistakes to make. These are really
enjoy
good.
everybody at home. I'm not sure if we need uh, extra parentheses for tuples. That's just a syntax detail. But I see what you're saying. I think my boundary conditions are right, and the data type I'm putting on the queue is right. In theory.
This is interesting. I don't think I generally write it this way. It might be
Okay.
right. Because, like, everything. Okay, well, obviously there's an additional thing you have to care about, right? You did not check for
Yes.
visited inside the BFS.
Right.
But I'm going to assume that you mean all valid nodes only get popped. So if this is a valid node, and if you're only moving in the direction of I, and if the direction of I is greater or equal to than 0, then assuming your J is correct, right? And if you're only popping visited nodes, yeah, I think this is a valid construction. I don't think I've ever
Okay.
written it this way, but I think this is valid.
There's likely good reason if you've never written it this way, but that's what just seemed obvious to me. And
No, that's fine.
before appending, we need to check that they're not visited, right?
Yep.
Is that what I need? Yeah. So
You definitely need to check that, yeah.
right.
I think this one reason
Repetitive.
why I use a for loop is because I don't have to write not in visited as many times as there are neighbors. But no, this is good.
Okay.
I'm also not sure if this is valid Python syntax in order to do that. Oh wait, no, yeah it is, because yeah. Yeah, it should be valid.
And those, and then
You should prune while you're at the parent. Just as a habit.
prune.
I don't think it probably
at
matters
the
in this problem, but yeah.
So help me out with what you mean by that.
Yeah, so you are pruning at the parent, but
Mhm.
so you want to update the visited node, I guess is what I actually mean. I mean visited set, right?
Mhm.
So when should you update the visited set? I would actually do that while you're at the parent. You don't have to in this problem, but as a habit, I just do that. So in all your q.appends right here, you can also have a line above or below that where the visited gets updated with that. And this prevents that same node from getting enqueued again if another node dequeues and
Right.
say, oh hey, that exact I minus 1 comma j is not invisited because it hasn't been popped yet, right? That's kind of a space issue you might run into.
By not doing it that way, I can blow up the queue, you're saying?
Yep, the queue can get pretty big. This doesn't matter so much for this problem because for each node there's only 4 edges and it's bounded. But when you deal with graph problems that may have more than just a constant number of edges over the vertices, yeah, it can become an issue.
Okay. And I don't remember how to add something to a set. What is the name of the method? Is it
It's
insert?
just add.
Okay. Of course, pick the most obvious thing. Okay, yeah, this is a very
It works. I like it.
it's a very repetitive way to write this out. There's got to
That's
be
fine.
a cleaner.
Yeah, that's the for loop that I would that I write
Okay.
usually for this basically. But no, this is essentially it. I mean, you only arrive at like hyper optimized solutions after optimizing like, solutions that aren't the cleanest. Even when I do problems, like usually it's like I don't write the cleanest solution first. Like I go back through solutions and I'm like, this is too confusing. I have to clean it up in order to present it to you all.
Okay. So
Yeah,
the
these look right.
verbose version.
Yeah, this looks right.
And we need
Oh,
to.
you also
Uh-huh.
additionally need to care whether like you go out of bounds, right? So
Go
this is
out of
just a
bounds.
basic BFS traversal right now. But remember in enclave, right? If it's at a boundary, then we need to record that, oh hey, this BFS went out of boundary actually. Oof, how do we do that here?
Oh, well. That's what all my conditions are checking for.
Yeah.
So I wonder if I did something like this. Like, well, like, something like this, where instead of doing all the bounds checking again, will that work?
I think. Okay, so there's a few complications, right?
Okay.
Because you can get stopped out by this visited, right? It might have nothing to do with your indices being out of bounds.
Right.
You might just have
Right.
like visited them. That's one complication. I think another complication is it's possible to set this flag when if I minus 1 is not greater than 0, like you go out of bounds to the left, right? This is going out of bounds. Oh wait, sorry. This is rows, right? I is rows. So this is going out of bounds from the top, right? And separately, this is going out of bounds from the bottom. So it feels like each of these little conditions might actually need its own little else and not be coupled with the visited portion.
Okay. Okay.
I think actually this is a really good refactoring candidate as is right now. Do you want to refactor this, or do you want to actually just keep these branches and rework with the branches? We can roll it up into a for loop if you want.
Why don't we try that?
Okay, sure. I think this will make some of the logic a little bit simpler because it'll allow us to name these tuples this way. So, hold on. Yeah, browser slow. Okay, so for basically, now we have our I and our j, right? So now we want to care about our neighbors. And to get our neighbors, we're going to do these calculations. We're going to do them this way. I guess I would call them di and dj. Because this is how our I and our j are going to change. I just generally like type them out in some order. As long as only one of them is minus 1 or 1 and the other one is 0, like I otherwise don't really keep track of what I'm typing. Okay, just going to name this next I and next j, and it equals I plus di and then j plus dj. If you want, you can name this like coordinate. I would screen this out first. So if chord not, so you could do chord not in visited, and then you could nest inside that if block. Because I like to avoid nesting, I generally do it in this type of way. If chord in visited, I'm actually just going to continue. That way all the code that I look at isn't indented as much, and
Okay.
I can feel free to just assume that, hey, all these coordinates are potentially valid because they're not visited. I then roll up like all of these conditions. So if next I is greater than equal to, and because I do it via negation, like I actually plan to write an expression and then continue.
Okay.
So I'm actually going to have kind of like the reverse ones that you do. So if I minus 1 is less than 0, that's a condition where I might continue. But we also have to keep in mind, for this problem, we don't necessarily only want to continue. We want to actually do something else. We want to specify something about this enclave, right? What did you name it? You said flag. I'm going to make that false, right? So if I minus 1 is less than 0, then we went out of bounds, right? If I plus 1, what's the expression here? Greater or equal to...
No, okay. Right,
yeah.
Yes.
You could also technically just write double
ones.
equals, because you only increment by 1 each time. So you have to cross through the length of the grid if you're going to get higher than that. But because you're not going to queue any nodes, double equals is just fine. Or j minus 1 is less than 0, or j plus 1 equals the length. I'm just going to take any old row and get that length. So that's my conditional right here. In Python, I actually found it quite annoying to write multi-line or statements, but you have to wrap them in parentheses if you're going to do that. So yeah, that's my conditional wrapped around in parentheses. I'm going to flip the flag, and I'm going to write continue. Otherwise, what should happen? Do you want to take it from here?
Yeah, so we already checked whether it's visited, and we already checked the boundaries, so we just need to enqueue. That's all that's left to do, right? And next, this pair next I, next j iterates through an increment in each direction, as long as it's valid. So it will just be.
Or you can just use chord, because I named it.
Oh, right. Good deal.
Is there anything you need to do with another data structure?
Yep.
I don't think I've solved this problem using BFS before, so we'll see if this passes.
Okay.
But okay, so far so good.
Okay.
Yeah. In addition to this, we now still need to like figure out to increment the enclaves, right?
Mm-hmm. So we wound up with flag false when we got to a boundary, and we've sort of doubled. We're taking care of two things though, really, because what we need is to check whether something's at the boundary in the first place. We need that so we don't go out of range, but that's also the condition for setting our thing true or false.
Mm-hmm.
But something else needs to happen.
There is one other thing I totally forgot, but yeah, we need to figure out to actually increment the enclaves. We don't have code for that. You kind of have this right here, but we do this conditionally, right? Also, one thing that I missed, well, one thing that I forgot to mention earlier is that like there should maybe be one more condition here about when to not traverse, right? And I'm also going to put that condition here. See if you can remember what that was.
Another condition on when not to traverse besides whether it's visited. I mean, and we're checking whether it's at the bounds. So I don't remember. If grid at next step. Oh, if it's a 0, we don't do anything.
Yep.
Yep. We don't want to deal with it at all. And
This
I'm
will
going to
also
delete what I wrote before.
We also probably need this case inside this for loop, right? Because imagine if you just enqueued a 0, but it was right next to a bunch of 1s, right? You might not want that to happen. So I might also put that up here, right? If column, because I have a reference just to the value, equals 0, just continue, right? No need to process.
Okay. And then I think it's after doing our whole BFS. Right. So, sorry, going back, this is an alternative to saying, to what we were talking about at the beginning of like finding a 1 inside the grid. We're just saying the inverse of that. If you don't find a 1, return or continue out top. And I think that's what I intended to set up initially.
Me too.
Okay.
Yeah, I think that's what you meant. I think this is fully fleshed out. Darn. Spaces versus tabs. Now let's see if this compiles. Oh, it compiles. Sweet. Okay.
Incorrect.
We got the wrong answer for one of them. We got the output as 1. Oh, I misinterpreted the problem. This is the number of land cells in the grid for which we cannot walk off the boundary.
I did that too. Okay. So that's gonna require a slight rethink because that is gonna have to happen inside our search, I think.
Yeah, it'll happen inside the BFS. We'll just count the number of land cells, right? Instead of enclaves plus 1, if we know the number of cells that have been enqueued in the queue, you know the answer. As long as the flag is true, of course.
Will that not work if we initialize to 0 inside?
I
Because-
do not think that will work
Okay.
because well, for one, this if is after this while loop. It might be hard to tell from this indentation, but you have equal indentation of this while and this if. So cells will actually not be defined, right, when you access it here,
Right.
because it only exists in this while loop scope.
Right.
I see what you're trying to do, though. You're trying to increment the number of cells. This only happens actually when you're enqueuing children, however. So what if you had a case that looked like this, where you had just a bunch of zeros and you had this 1 right in the middle? You wouldn't have any children whatsoever to get to this point, right? Because when you enqueue, it's because you found a 1, right? So I think this line is correct, but where might you move this line?
You line to increment the number of cells.
Yeah. How
I
many?
don't know because
How many
I thought
nodes?
it needed to increment each time we enqueue a cell.
So you can do it this way if you want. You might, okay. So you can do it this way if you want. I would recommend maybe initializing cells outside the while loop.
Yeah.
And this if block, I think it was good where it was, right? Because you want to give your BFS the chance to fill in all the visited nodes, right? Because if it doesn't fill it in, the outer for loop is actually going to run BFS and maybe connect up to something. And maybe that would work, but it's just kind of weird to do that. So I feel like it's a lot cleaner to just have this if block where you had it. And if you were going to, yeah, so you might initialize cells to the size of this queue. You can actually initialize it to just 1 out here if you want to do that, and then your logic down here would work fine. An alternate approach is just to initialize cells to 0, and how many times are you going to pop? You're going to pop for all the number of nodes, so you can just do cells plus 1 right here. So both of those ways work. Yeah.
Inside the for loop? Or
right under after you pop, right? Because how many nodes are you actually going to pop in your BFS? You're only going to pop the exact number of nodes that are connected, right? So yeah, both of those
Like
ways work. Yep, both of those ways work.
And not that.
This would work. This would work. You just have to initialize your cells as 1, right? Because
Right.
you need to take care of the parent node. And this example that I have, this drawing that I have, shows you that, like, yeah, just be careful about that.
Okay. That's kind of subtle to my eyes to see that. But definitely don't want both. That'll give us the wrong answer.
Yep,
So
you don't want both.
I think what you're saying makes increments on pop. Yeah. No, I would have totally missed the miscounting, not counting the parent. Okay.
All right, I am going to try and submit this and just write in the code that you had. Plus equals 1, enclaves, just add cells. Oh, I messed up with my unindent. Oh, why? Because it's all spaces. Yeah, so we're gonna copy my tabs over, because LeetCode does not, well, Python doesn't allow you to mix tabs and spaces, I believe. It throws an error. But okay, I think the indentation looks okay. Oh, still got it wrong. How did I get it wrong? Oh, I have 4 now.
Overcounted.
I overcounted by 1. So how did I overcount? So did this flag actually, was it not triggered correctly or what? Well, in times like this, I am just going to print out the starting coordinate of where that happened. Oh wait, inconsistent use of white space. Ah, yeah, it's eating me for breakfast. I am actually just going to change all the tabs into white space. Let's see. Gonna change the tab to maybe 4 spaces. Okay. I did a regular expression replay. It's just in a text editor that I use. And hopefully this works. Okay, cool. So it compiles. Okay, so it said that only 2, 1 was that valid. So we go down the rows, right? So we scan this way. This 0, this 0, this 0, this 0. And yeah, so this is strange. What? It should be 1, 2. Should be ij. Why is this printing out 2, 1? Did we increment this weird? Okay, so we enumerate the grid. So this is each row. You enumerate the row, that should give you the I and j. Start the deck with I and j. But this is very strange. This is our starting node. Okay, we explore 1, 0. We explore row 1, 2. Okay, that's good. Oh wait, did I? Oh wait, this is the wrong indentation. Wait, no, it is the right indentation. Why would it print? I'm exploring 1, 2, but it's printing out 2, 1 for ij? Where did we flip things? Oh, I see what happened. Okay. This happened when we reassign the values of I and j right here. This is a... Yeah, that's what happened. Okay. I'm gonna call this R and C. Just like if you can reassign the names actually. It's kind of funny. Okay, at least the printout is correct. All right. It's because when you do this, you reassigned what I and j were. Wow, that was a cool gotcha. All right, so now we have 1, 2, and we know we are adding the enclaves from 1, 2. But where did we go wrong? So I'm gonna print I, j here. I'm just gonna say visiting. Okay, I only care about this portion. So we visit 1, 2, right? Because we explore this as the like representative node of starting here. Then we visit 2, 2. That's this node right below it. And then we visit. Oh, we go back. Ah, classic mistake. I'm so glad we explored this. Okay, so here's what happened.
Okay.
Do you see the problem now?
It didn't get added to visited at the right time.
Yeah, that's right. Because when we do it like this, we need to actually add this coordinate to the visited. Otherwise, we can backtrack to it. Oh wait, that messed up another problem. But hey, the first problem went right.
Huh.
Visiting 1,
Okay.
2. There's 2, 2, and there's 2, 1. Right. So 3 things for this representative node. That's good. That's what we expected.
Right. Okay.
This case, however, turns out we were wrong somehow. We actually outputted something, and why is that?
2 instead of 0.
Yeah, so I'm just going to mark where it saw an enclave. So enclave found at 1, 2. So 0, 1, 2. Wait, no, 0, 1, 2. That is very strange. I would have expected when we did this exploring. In fact, we should not explore this. We should not explore 0, 2. That should not happen, right? So how did that happen? Oh, this condition is wrong. You need not in visited. I think before we had not
You can
something.
just say not. Oh, it's just a weird Boolean, a truthy thing.
Oh wait, I'm wrong.
Okay. Not same answer.
Same answer. So the same kind of wrong that we had before. It's very strange. Okay, so we explore row 0, first element in that row. Cool. We visit this 0, 1. Which, how did we not visit 0, 2? In Sooth, I have no idea. Guess we'll have to like print out more, debug a bit more.
Can you copy the current state of it back into the Google Doc?
Yeah.
And if you want to throw in the towel for now, that's fine by me, but you gotta go.
Okay, I pasted it in.
Okay, thank you.
so strange.
That way we just have this both the same thing to work off. So it. I mean, it shouldn't even. I'm not sure I see where the print statements are, but it should explore 0, 1, but it shouldn't visit 0, 1, right?
When we pop, that's where we print the visiting.
Okay.
Okay, interesting. When we explore 0, 1, we do not find the neighbors whatsoever. The neighbor 0, 2 is never found. I printed that like to record all the neighbors, and it's like, oh no, didn't happen.
So when it's finding bad nodes, it's not continuing the search to find the rest of the bad nodes.
It should. I wonder what we'll realize the mistake is. So, let's see. It definitely sees 0, 2 as a candidate. And it will, but when it goes exploring, yeah, I guess 0, 2 never makes it there. So somehow we screened it out. Oh, I realize what it is. Ah, so silly of me. This is really the next coordinate, right? We were comparing against the parent coordinate, right? So it got all jumbled. And boom. Wow, this one is wrong now. This is crazy. It's been whack-a-mole. But I think this logic is much more closer to correct than previous.
Okay.
Why is the output 0? I'm going to remove some print statements. Alright, so explore 1, 0. Then you explore 1, 2. And apparently we found 0 enclaves. Oh, right. Because obviously when you did that calculation, it's next I and next j, right? This represents the already next coordinate. Okay, now I feel like that's good. Okay, sweet. That was a lot of debugging.
So then what was the problem with having I and j incremented and decremented before?
Is it okay if I overwrite this?
Yeah, sure. If that's what next I and next j represent.
Okay, so we had a few problems beforehand.
Okay.
One of them was when we destructured this, we reassigned what I and j were, right? That totally messed things up, right? That was silly, kind of funny to make that mistake, to be honest. Yeah, anyway, just watch out for that.
Yeah.
But if you have a linter, it'll show you like, oh, hey, you're shadowing a variable. You've already reused that. So if you were doing real life software engineering, like, that probably you would have caught that much earlier. Anyway, when we did this while loop, right? Keep in mind that we already did the calculation for what this next coordinate was, and before then, we forgot to update these variables, right? This was I like -1 or whatever, right? I still was like copy and pasted from your conditions without actually updating next I and next j. So what I did was then, I'll just like basically in my mind string replace all the places where I had I and j with next I and next j. But then we had -1 and +1. It's like, wait, no, that's what the entire thing represents. And that's how we got to this representation. So yeah, this is the actual coordinate, right, from doing the calculations. It's rolled up into a for loop. This is what you check. We, set the flags incorrectly because of that one calculation. Another thing was we had another mistake where we did not add this thing to the visited queue, right, in the beginning. So yeah, in my template, I explicitly say, hey, you pass in the queue that you have and make sure that they're all visited. So yeah, we forgot to do that. We made a mistake. At least when you do BFS in this way. All right, I am going to just submit this. I have confidence. And cool. Got a green submission. Some ways to speed this up, of course, is instead of using a set, you could use like a grid or whatever. I believe it is also possible to use disjoint set union on this problem, which is going to be actually faster, but only in constant time. Like, I don't think it's going to be a different time complexity. DFS is actually, sometimes for these problems I use DFS because I find it a little bit simpler to write, and I just write that recursively. But yeah, good job. Like, the devil's in the details. And I'm glad we made the mistakes that we did because they're important to make to help you see where things might have gone wrong.
Right. Well, thanks for debugging. I would have given up sooner. And I take blame for creating the conditions for the mistakes.
No, it's okay. I'm glad you learned stuff. So yeah.
Yeah, this was fun.
Alright. I'm gonna
are you still recording?
Yeah, I am. I probably won't edit the video. Here's some homework practice problems. You can try a number of provinces. It's kind of like the problem that we just did. There's employee importance. This is a tree-based problem that you can try. Pacific Atlantic water flow. Yeah, this is an interesting one. It can be solved in multiple ways. There's these other ones. I actually tried to use an SPFA here. It passes and it's kind of slow. Dextra is going to be faster, and we'll talk about that next week. If you want to practice like keeping track of like metadata on your nodes, I think this is a good problem to practice with. And I have a couple of challenge problems. They're hard. But that's it for the lecture today. It was the longest one I've ever had. But thanks so much if you watched it to here or were with me live. But you can send me questions or tell me how to improve. And have a nice day.